right, we're going to go ahead and start in our Unit 5, our information to continue with the descriptive statistics. We're going to talk about what this thing called standard deviation is. You might have heard it before, and here were two little introductory videos that you watch to kind of get an idea of what's happening. And I'll reference those a little bit. Like how tall is somebody? Well, or how different is somebody's height compared to the others? Like LeBron James and Yao Ming were referenced in the first video. And so we use that standard deviation to kind of determine if they are an unusual height. And so we will go into that. The second video, of course, was taking you step by step through how to calculate that standard deviation by hand. And we will do that a few times, but later then we'll do that with calculator and not have to get bogged down in all of the calculating. So let's go ahead and move on to our notes. First, we know about range, the highest minus the lowest, that total spread, and we know about that interquartile range, that middle 50%. So standard deviation is going to be the next measure of how varied the data is, how spread out. The bigger the standard deviation, the more spread out. The smaller the standard deviation, the more closely clustered around the mean. That is because the standard deviation is the average distance from the mean. So how far away are all of these pieces of data on average from the mean? All right. They talked in the video about the two different ways to notate this. We'll deal with samples probably more here at the beginning than we will with the population standard deviations. And those will be notated with S. I typically write SD because sometimes S's look like 5s and I don't want them to. So I a lot of times will do SD instead of the just S. All right. And so we may come back to this, but this is a very, very scary looking formula. And we'll break it down and we'll learn what all these little pieces of or all these symbols are. And we'll learn how to calculate that standard deviation, figure out on average how far is the data from the mean. Okay. But before we do that, let's just get that basic idea. Standard deviation is that average distance from the mean. The farther away the mean is, or farther away that the mean is from the data, the bigger the standard deviation. If it's more closely clustered around the mean, then you have a smaller standard deviation. So I want you to take a look at these two data sets, data set 1 and data set 2. Data set 1 and data set 2 have very similar means. Their average, 32.3, similar to 32.8. Very similar means. But look at the standard deviations. So we want to say, whoa, why is that standard deviation so different on these two? So I want you to look at these numbers in the sets. See if you notice a pattern. Okay, and then we're going to have somebody, I would have somebody tell somebody something. So if you want to stop and think about that for just a minute, let's do that. I see with data set 1, I've got all these numbers in the 30s. Data set 2, wow, I've got numbers from 10 all the way up to 58. So these are quite a bit more spread out. Definitely, if I was to graph these on a number line, they would definitely be much more spread out than all of those numbers that were right there in the 30s. That is why the standard deviations are so different. These numbers here are closely clustered around the mean, so the standard deviation is 2. Here, these numbers are much more spread out, so they are farther away from the mean of 32. So that's a much bigger average distance from the mean. All right, so hopefully you noticed that. So let's now get into this scary looking formula. And this one right here even looks a teeny bit different, but let's take a look at this first part. How would you get the distance from the mean? Okay, so like if I want to see how far away is somebody's distance from the mean, first I need to know what the mean is. Okay, so let's look at this set of data. So we're going to kind of practice through this. A lot of times I'll do this with students standing up and we measure their heights, and we see what's their average distance from the average height. I put them in order from least to greatest. So here's the sample here. The mean was 40. And then, so here's 3 people on the left of the mean and 3 people on the right of the mean, or 3 pieces of data to the left and to the right. Okay, so we notice that if we see how far away each piece of data is from the mean, okay, because we want to average those distances. So I'm going to do that 30 minus 40, and that's how you get negative 10. 20 minus 40 is how you get negative 20. 10 minus 40. So 10 is 30 below. That's why it's the negative 30. And 20 is 20 below, and 30 is 10 below, and so on. Then these are the positive distances. So that's what this is right here. X minus the mean. So you're seeing how far away that data is from the mean. So look, it's got this thing squaring. Why are we squaring that? Well, let's take a look. If I took these numbers, and this is a fact that you actually do need to know. If I took these numbers, negative 30 and 30, negative 20 and 20, negative, and I added those together, because you know how you get mean. You add them all up and then divide by how many there are. So if I took all of these numbers right here and I added them all up to divide by then 7, I guess, I would get 0, because they would cancel out. And that's always what's going to happen with your standard deviation, because the average distance on the bottom is the same as the average distance above the mean. So the average distance, those will always sum to 0. So not instead of taking the absolute value, which that's something else, okay? And I could go in depth as to why we don't just take the absolute value, but I'm going to leave that be for right now. So instead of doing that, we square them. So to avoid having that sum be 0, we're going to square those standard deviations. That's why the formula has you doing these differences and squaring them. So then we're going to add up all of those squared distances. So we're going to add up 900, 400, add up all those squared distances. We add them all up and we get that total sum. Now, what would you do if you were adding up all your data to find the average? Add it all up, divide by how many pieces of data there are. So that's what we're going to do. But when we have a sample, we actually divide by n minus 1 instead of n. The reason being is because it's a sample and we have to allot for more variability happening than in the population. So I had to be a little bit on the safe side. Anyway, so there's a lot more involved with that, but I'll just leave that there for you, telling you there is a reason why we're just going to then, in this case, instead of dividing by 7 pieces of data, we're just going to divide by 6. That will make this average distance from the mean a little bit bigger and on the safe side for us when we're estimating. So we have this 467. So that is this thing called a variance. And we need to know that this thing called the variance is what you're getting before. See, look, that's what's underneath this. We took this, we summed them all up. That's what that sigma is. That's what that capital Greek letter sigma told us to do, is sum up all of those squared differences, and then we divide by n minus 1. And once we do all of that, that's the variance. But to get the standard deviation, you have to then backtrack it off. And whereas you had previously squared the data, now let's unsquare it by taking this square root. So that's how then you get it down to that standard deviation. So the average distance from the mean for those 7 numbers was 21.6. Okay? All right, so now here's some more examples of standard deviation in the real world. Let's make sure that you kind of have a good understanding of what this concept, that's the most important thing, what this concept of standard deviation means in the real scheme of the grand scheme of things. Okay, we'll do a little computing here in a minute. Okay, but we don't want to get too bogged down with all that computing. So here are some rushing leaders from the 2000 season. Okay, and I don't know if these were in the NFL or exactly what those were. I think maybe so. And so what they did was they took their rushing yards that they had. These were the top 10, their top 10 games. And so then they got what their average rushing yards were and then the standard deviation of their rushing yards for those um, running backs. Okay, is that what these were? So then here we go. We're going to examine two different players. We're going to examine Stephen Davis and Corey Dillon. Because what's interesting is you see Stephen Davis had a mean, an average of 87.9. Corey Dillon had a mean of 89.7. So similar averages. Okay, so that's important. We had similar averages, but what's very different about them is that standard deviation. Okay, so very different standard deviation. And so we want to talk about, well, what does that really mean when you're looking at data? Okay, sports so much all about data, and this is a big start to it. So here is what Stephen Davis's distribution would look like. Here's what Corey Dillon's distribution would look like, much more spread out. So my question to you is, who do you think would be the preferred player if on average they're about the same? So see, Corey Dillon, he could get way, way high, or he could like do really, really bad. And every year I've asked this, I get the same answer every year, that my guys on the football team would prefer to play with Stephen Davis because he is much more consistent than Corey Dillon. You can count on what he's going to do for you each game. So you know better what to expect. And that's because his standard deviation is smaller, because he is more consistent, whereas Corey Dillon is all over the place. So he has a much more varied standard deviation. All right. So now let's move on in to the next page and actually do a couple of these computing by hand. So here we go. This is the consumer reports of some gas mileages for these five Subaru cars. So I first went ahead and I put them in order and I added them up and divided by 5. So here you have that mean of 19.6. And then if you do look at the median, okay, that 19 would be the median. Q1 and Q3. Interesting. Actually, I think if I did this in my graphing, if you did this in your graphing calculator and got the 5-number summary, um, you could say that Q1 would be 17 and Q3 would be 22 and a half, because it'd be the middle of that. So that'd make you a bit different. In fact, let me just go ahead and put that in there. So you may see that the Q1, if Q1 is 17 and Q3 is 22 and a half, okay, so that's fine. What happened was, the reason this was different is because sometimes some textbooks use the median in calculating the bottom half. So the middle of the bottom half was 18 if you use that median. But if not, you get these numbers here. So with these numbers here, of course, then our IQR is a little bit bigger. It's 5 point, what is that, 5.5? Okay, so here we have, and so we'll keep that in mind as we're going through and looking at things, because that's a measure of variability. Okay, so let's move on and start now working through this standard deviation formula. All right, so here it is, standard deviation formula. First things first, and I've got it kind of laid out here. We're going to take a look at each individual observation. So what I have done is I've taken each individual observation, and I'm going to kind of get myself a piece of data something that's a little bit more movable. Each piece of data is right here, and so I listed all 5 of those. Okay, so there were all the 5 different cars. Okay, I had an extra space down there. All right, then the next thing that we're going to compute is this. how far away is each piece of data from the mean? Because we want to get the average distance from the mean. So that's this, x minus x bar. X bar is the mean of x. Okay, so you may or may not know that. X bar is the mean of x. And so that's what we had calculated up there as a 19.6. So I want you to fill in each one of those. So we're going to end up with, let's see here. Let me get myself one more of these little guys so I can keep this third column covered. All right, so we got, there is x minus the mean, and there's how much that is. So it was 3.6 below the mean. Here's the next one, 18 minus the mean, and there it is. And the mean, or 19 minus the mean is that. 22 minus the mean is above, and this one also is above. So there's our distances that each piece of data is away from the mean. Well, what you should notice is that if you summed all of these together, then they would add up to 0. Okay, that's why we do what then? That is why we squared them so that they would not sum up to 0. So here we go. I'm going to take this value and square it. I'm going to take each value and square it. So there are all of these values, distances squared. All right, take a look at our formula. After we square them, then we got this sigma. Sigma is a Greek letter, capital sigma, for summation. So sum them all together. So that's what I'm going to do with all of those pieces of data there. So I'm going to sum them all up. Here we go. And the sum of all of those squared differences is 33.2. So when I then divide by n minus 1, remember we're dividing by n minus 1. What is n? Okay, I might have just jumped to that. N is the number of pieces of data. All right, so n is the number of pieces of data, so that's 5. So n minus 1 means I want to divide by 4. So there I do that, and that's 8.3. So now I've got my variance. That is called the variance. So that variance is 8.3. And then to finish it out and get that standard deviation, what does it say we do up here to get this standard deviation? We unsquare it, so we square root the variance. And so that is 2.88. So the average distance from the mean is 2.88. All right, so that is the standard deviation. And so now we're going to take a look at a similar situation on the next page. But we're going to take a look, and I want you to practice with this. Suppose that the Impreza is now a hybrid vehicle that has a gas mileage of 44 miles per gallon instead of 23. So look, this 44, look at how this 44 compares to the other pieces of data. How does that kind of fit in? Is it similar, like the 23, or is it quite different and much farther out than what the other pieces of data are? It's more unusual. Okay, so we're going to talk about that and see what that does. So I'm going to have you stop right here. We're going to have you recalculate things and let you work through that and see how you do. So I'm going to let you pause, and then we'll come back to check your answers. All right, so let's take a look at that. Let's see how you did. You had to recalculate the mean. So the new mean is 23.8. So it definitely was affected. The mean was affected. Look at that median. It's still 19. Okay. Now, interestingly enough, is that our IQR, the original way that I had done that, was not changed. Okay. Now, and it's because this was such a small data set, if I had done it the other way where I went from 17, see, this would now be at 33. So that IQR would have changed. And that's because it's such a small data set. If this had been a much larger data set, then it would not, that stranger up on the top end would not have affected that location of the IQR. Okay, it's probably why this was done this way. Because we did want to keep the number of pieces of data small at 5 since we're doing this by hand. Okay, so here we go. We're going to put all of our pieces of data down. There's our 16 through 44. And what's the first thing that we're going to do? How far is each piece of data from the mean? And here we go. So a mean of 23.8. So here are all of those distances from the mean. And what do all of these distances sum to? If I added them all up, they would sum to 0, which is why we square them. So here are those distances squared. Distances squared. Much bigger numbers. You should notice that these are much bigger numbers because that mean changed. So that average distance from the mean is also bigger for all of these. All right, so we're going to sum up. That's the sigma, and I got a sum of 528.8. And then I'm going to divide by n minus 1. So I'm going to divide by 4 pieces of data. That gives me a variance of 132.2. But then I get the standard deviation by square rooting it, and I get that 11.49. Okay, we want to compare all these things. Look at the median and IQR, unaffected by that change in the outlier. But what about the mean and the standard deviation? They were affected. So explain how this measure of center being the mean or the median, were affected. The mean increased, okay? The mean increased, but the median did not change. The mean increased, but the median stayed the same. How about the measure of spread? The standard deviation in the IQR. Well, again, that average distance from the mean went up a lot because you had that outlier, but the IQR stayed the same. So, which measures of center and spread would you consider resistant to outliers? So let's talk about, what does that word resistant mean? Well, what can you think of that you hear that? How about water resistant? If you have something that's water resistant, what does that mean? It's not affected by the water. Okay, so we want to know what measures of center are not affected by the outlier. If we replace this word resistant, not affected by the outlier. Which one was not affected? Median was not affected. Which one was affected? Mean was affected. Standard deviation was affected. Median and IQR were not affected. So we're going to see at a later time that we'll have to make a decision as to what's the best measure of center and spread to use. Should I use that median and IQR to represent the data, or should I use the mean and standard deviation to represent the data? And knowing how the data is affected is what plays into our decision as to which measure we should choose to use. Okay, so that's another key point. All right, so hopefully you have learned all about the measures of center and spread, or the measures of center and spread, and this idea of standard deviation. And so then tomorrow you will get to practice doing some problems, first computing that, and then kind of just doing some conceptual ideas about standard deviation.